The next talk will be efficient, non-interactive proof of RAM programs with MPC-in-the-Head zero-knowledge system. The talk is by Cyprien de Guilhem, Emmanuel Orsina, Tito Tanguy, and Michael Barbier, and Cyprien is giving the talk.
Thanks. Yeah, so all of us at COSAC, also special thanks to Akira, who did a great job of presenting MPC-in-the-Head. So that's a third of my talk gone, basically. I'm going to be talking about what a lot of people have been talking about at this TPMPC already today, is how do we start saying stuff about RAM programs or computing stuff about RAM programs, because circuits are nice, but people in the real programming world, they don't work with circuits. So it's kind of up to us to adapt to this kind of stuff. And today I'm going to talk about this little work we did about bringing some techniques to the public coin world, because public coin is better for like non-interactivity and public verifiability, and that's why we care about it. And I'm going to spend a bit of time talking about MPC-in-the-Head. I'm going to bring a slightly like historical perspective to what Akira already said. And I'm going to highlight a couple of like paradigm shifts that were very good for MPC-in-the-Head, and that kind of happened here as well for RAM programs. So to get started with that, this is the head of MPC-in-the-Head. We've already seen that the prover has these kind of virtual servers, and it's putting in the witness inside the computation. The servers output the result, and you get this transcript out of it. And then you get a zero-knowledge proof by committing, challenging, and opening the commitments. So the original idea was that the prover would simulate a protocol that computes the circuit you're interested in, right? So we had the first theoretical construction, then we had all these protocols, ZK-BOO, ZK-B++, KKW, and then barbecue. And gradually we were moving, like we had Boolean things that were good for Boolean circuits, things that were better for arithmetic circuits. And at some point there was the great idea that while the prover can already compute the circuit, why do we need to do it again? It's much better if we can just verify that the circuit computation was done correctly. So the idea here is that the prover pre-computes all the outputs of the nonlinear gates, especially the multiplication gates, gives them to the parties, and then the parties can just run one big verification protocol to make sure that the prover was not cheating. So now at the beginning, this was used to do verifying the correlated randomness that the MPC needed, but in the later protocols like Banquet and Limbo, we just verify the multiplications directly. And so what we can do is when we want to try and apply MPC-in-the-Head to a new situation, we can take whatever circuit we're trying to prove and try and like express it in terms of checking multiplicative relations. And once you've done that, you can just throw it into one of these systems. So when we did this, we achieved quite efficient signatures, for example, based on AES. And we were kind of wondering what next. And we saw that we could look at RAM programs. So zero knowledge of RAM programs was very recently shown to be possible in using constant overhead. So the work I'm going to be talking about is from last year at CCS. And there was a similar kind of observation that you don't need to compute the RAM access as the computation is happening. You can just check, you can just trust the prover to say, these are the values that I accessed, this is the order I accessed them in, and the verifier only has to check that the prover is being honest about this. And because usually computing a permutation when you want to hide your access pattern takes n log n cost, this is great for achieving much smaller overhead. So the way this works is we assume that there's some kind of zero-knowledge proof box in between. So this is a private coin protocol. And so the prover and the verifier are both sharing kind of a state. And the prover starts by inputting the RAM values. So these are kind of like the initial RAM values of the computation. It asserts that it can prove the execution of a program pi on this RAM. And then the verifier asks to check that this execution is satisfactory. So the way we then prove RAM is that the prover will then tag on an array of accesses that contain the information in ZeroKnowledge about which value is being, like which address is being accessed, what's the timestamp, what's the operation, and what's the value. And not only will it prove the execution of the program, it will also prove the execution of this checking circuit that verifies certain conditions. And so when the verifier queries for verification, it checks both conditions. So to get into the detail, the lists, so we have a list of essentially tuples, which contain these informations with the address, timestamp, operation, and value. And the circuit will then check that every address that is being read was first written to. We can't be reading some value that didn't exist before, because that's a perfect way for the prover to inject information that shouldn't be in there. And that every read operation is consistent with whatever was previously written to that operation. And so the way this circuit works is that you trust, in quotation marks, the prover to input a permuted version, of this list, where it is doing the sorting. So you trust the prover to sort it according first to address, so that all the addresses are next to each other, and then by timestamp, so that all your accesses to the same address are ordered correctly. And that's much, much cheaper than having your MPC parties kind of, compute and order your permutation secretly. So then all you have to do is check that this is indeed a correct permutation. And then you go through and do a linear scan and just check pairwise that each value, all the conditions are satisfied. So the way this works is you have these two lists going in. And so in this particular private coin system, because they work over fields of characteristic 2, they can prove Boolean statements about their values. And so all these comparisons and equalities where you will trust me that these check the consistency requirements about reading and writing and ordering and stuff, they can just bit decompose and check these fairly efficiently. So once you've checked all these conditions, you need to do a permutation check, and permutation check are done much more efficiently using an arithmetic circuit, simply with the observation that if you permute the roots of a polynomial, it's still the same polynomial. So you create two polynomials based on your two lists, and you probabilistically check that they are the same. Now, something else where they can take advantage of the characteristic 2 of their field is if you say, for example, that this tuple contains 4 32-bit values, you can just very easily write these into a single 128-bit value and create your polynomial over that bigger field and check it. And that tuple, like proving permutation of these packed values, is the same as proving permutation of tuples in a coherent manner. And so the problem is that both this and the previous Boolean technique only work well for these kind of private coin and binary fields. And when we considered the challenge of adapting these techniques to the public coin model, well, we couldn't do that. So how did we get to public coin verification of RAM access? Well, we designed this C-check so that we could use a single field without all these conversions. And this goes through doing an equality check circuit. We can still reuse the permutation technique with the polynomial, but we have to do the packing a bit differently. And we have to use like a bound check to change the way we do inequalities. Now, the advantage is that eventually we can make it non-interactive. So just to go through the different circuits that we have, the equality check in ZeroKnowledge is as follows. So we can read this a bit like a speed style equation. And this is where we can see that knowing that the prover in MPC-in-the-Head is always there to observe the computation and inject values is quite a powerful tool. So for example, here we have X and Y, and we want this to compute in secret chat form this bit B, which indicates whether they're equal or not. So the prover can just observe that they are. And at the beginning, we trust it to introduce this value R, which has to either specifically be the inverse of the difference if they're non-equal, or if they are equal, it has to be a random non-zero value. And this is essentially replaces a complex, well, not so complex, but an expensive MPC operation to secretly test whether a value is 0 or not. So we just do this. But because we're trusting the prover to do their job correctly, we have to check that they're doing their job correctly. And we do this by asking also for the introduction of the inverse of that value R, and then asserting that this R times its own inverse is 1. And this checks that R is non-zero. So usually in MPC-in-the-Head, doing a multiplication costs proof size, typically. Doing an opening of a public value, because in MPC, sometimes you like to open to make your protocol more efficient, that also costs in proof size. So you'd think that multiplying, then checking that it's equal to 1 is a multiplication, then an opening. But actually, our MPC-in-the-Head protocols, they check multiplicative tuples. So it means that you can have an array of tuples that are X, Y, and Z, and they just check that it's correct. So rather than doing the multiplication and then opening, we simply put R inverse and this public constant 1 as one of our tuples to be checked, and trust that it will eventually happen. So then we actually have to compute the value of the bit B, and here the prover is trusted to input the result, which this time we have to make sure that it's a bit, obviously. So again, we can do this kind of multiplication equals constant check to make sure that that is valid. And we flip the bit because we'd like to have 1 for equality. For the permutation check, we can't take advantage of this bit packing technique. So instead we use an inner product compression. So the verifier samples a random value, and we use this to compress our tuples down to a single value. We introduce a bit of soundness error by doing this, because the choice of the value could mess up the error, but most of the time it's fine. And then we can do the polynomial check in the same way. And this is where the constant overhead comes from. I didn't highlight it before, because you're permuting, when you're doing your permutation check, you're evaluating a polynomial whose degree is the size of your number of accesses, essentially. You only need this many multiplications to evaluate the polynomial. So per access, you're only costing 1 multiplication at the end. And this is where you really get the constant overhead. Finally, for the bound testing, we, since submission, kind of realized that there might be more clever ways to do this, but this is the one we went with for the moment. And the idea is you do, again, a permutation check. So if you want to check that a value is between A and B, you write all the values between A and B, and then you append all the values you're trying to check afterwards. You again permute this array to order it by size, and you check that it's a permutation. And then you pairwise check that either the two values that are neighbors are equal or that they differ by 1. And in order not to do the equality check twice, we noted that they either differ by 0 or differ by 1. Your equality check is either 1 or 0. So in both situations, both of these values should always sum to 1. And that kind of reduces the number of expensive equality checks that we need to do. And finally, we open the first and last value because we know that our bounds need to be in our array. So we're not losing any zero knowledge by opening this. So then to give a little bit of idea of how much all of this costs. So these two, Bubble RAM and Francis et al., which was the protocol I was presenting, these two were kind of previous state of the art on zero proof of RAM programs, both in the private coin model. So we can see that we're working over similar sized fields. The middle one is slightly smaller. And in the access time, we see that our public coin technique is kind of comparable with the first one, which was a couple years ago. So we're not quite down yet to the super efficiency of private coin protocols because we have to stick with the public coin constraints that we have, but we're getting there. Hopefully we will keep working and reducing these. For example, we can prove something about 500 kilobytes of RAM in just about 15 seconds. And sometimes we don't really remember how much we can do with low resources, but one of my colleagues found that the Apollo mission used only 4 kilobytes of RAM and 72 kilobytes of ROM. So we could prove this in about 10 seconds today. If you want to make sure that NASA is doing their flight calculations correctly, then you can use our stuff. Yeah, exactly. We don't trust those pictures. We never know where they were taken, you know. So yeah, I mean, thanks to a great introduction on MPC in the Head, this was a bit of a shorter talk, but I'm welcome to take any questions.